Hello everyone, I am Taha Muhammad, USA Kurd. I tell USA it means citizen from Kurdistan of Iraq. Okay, today I will talk about Euler perfect box first way. Last time I think I talked about second way. This is first way, very important way, which is A, B, C, D, E, F, G belong to natural number. If and only if we have Euler perfect box. If you have Euler perfect box, it means all sides with diagonals, interior diagonals, should be integers. Where? In a box. And that box, we tell it Euler box, Euler perfect box, this one. A, B, B, do you see that? C, C is clear here, C. Then diagonal surfaces, we have D, diagonal E, diagonal F, this outside diagonal. Interior diagonal, we have this one, G. Suppose all of those integers. If one of them failed, not integer, it means we do not have the Euler perfect box. And this relation that I did put is very simple and unique, if and only if. Okay, let me start. Proof. Let those all are what? Integers. Does not include G, no G. Here I have A, B, C, D, E, F. I have two other letters I will use it, R and K. Integers, no G. I need to prove G is integer also. Okay. Let A smaller than B, smaller than C. As you see here. Part A. Okay. Then A not equal to R and not equal to K. What's R? This one. R and K, this blue one, maybe you will see it well now. K, R, K, and A, those three letters are not equal. B is what? B is A plus R. The height is A, and the width will be A plus R. And C will be A plus K. A plus K. Okay. When you cancel from those three inequality, for this inequality anyway, A cancel, you will get R less than K always. R less than K. But relation between A and R, we have three possibilities. A smaller than R, or A greater than R, or A equal to R. Later I will come to that in part B. Okay. As you see from this picture that G hypotenuse for this right triangle, and G square equals D square and C. This is C square. D square plus C square. Pythagorean theorem. D also by Pythagorean is D square equals A square plus A plus R, which is B first. This is B. Next page. I did substitute the D, became B square and C square. Another substitute, change B and C to AR plus R, A plus K. Expand. We got that. Okay. Add like terms. we got 3a, 1, 2, 3a squared, and continue. But I am thinking to make this 3, 4. How? I have to add a squared. Also, I would like to see 2ak as 4ak. How I do that? I will add 2ak and subtract 2ak. See? I add 2ak and subtract 2ak. I added a squared and subtracted a squared. This parenthesis value is 0. Okay. Now, this one will be 3 and 1a there becomes 4a squared. 2ak and 2ak is 4ak. And k squared is a k squared. Plus another parenthesis. Left who? 2ar left, r squared, and what? Minus 2ak and minus a squared. Clear? Okay. This one. Since g squared equals 2a plus k squared, what I did here, I took square root of first term, square root of third term, and put the sign of the second inside parenthesis and square it. Do you see that? Then, this one is still same. I name it equation 1. Name it equation 1. Okay. I am telling if this parenthesis value 0, that means guarantee we will know g square equal this square, it means a square. But how we know this is 0? When this becomes 0, that means 2ar plus r squared suppose equal to 2ak plus a squared. Like 7 minus 7 is 0. This suppose equal to itself, to same value, but different picture, observer. So this is r, this is k. This is r, this is a. How I know this is equal or not equal? Okay, we have two ways. First way is substitution. The 6th grade student can understand that. Substitute two expression. How you know they are equal? You will put, give number to A, give number to B, give number to R to K, then you will know they are left side equal to right side or not. This is one way. Second way, logic. What's this? I am telling, in order this becomes equal, left side equal to right side, suppose R equals K, and this R equals A, then I am getting what? I am getting A equal R equal K. Without this condition, this will not happen. A, R, K, suppose equals. If not equal, you will not get 0. And this is a contradiction. I cannot do that. Because from beginning, I told you, A not equal R, not equal K. Then, this parenthesis value, 2AR, R squared, minus 2K, minus A squared, this one, is not 0. When this is not 0, looks like G squared is still unknown. Is G squared, this is not 0. It means G squared, I don't know. It is square or not square. Like it is 8 or 9. 9 is square, 8 is not square. Okay. The important thing, I prove it, this one is not 0. Then what shall I do? I am telling G square, in this case, either a complete square or G square is not a complete square, like 8. Complete square, like 9. Okay. Second thinking. See, I came to equation 2. I am thinking, telling, okay, let this g square equal to ak plus unknown. Plus unknown. That unknown, negative, positive, we don't know yet. But logically it should be negative because this is, I need the answer should be a plus k square. This add what becomes square. And that square, for sure, it is belong to natural number square. See, n sub square. I name it equation 2. That means you know here for 100% the g square, if we find right question mark value, then we will get a square of this equation 2. Now, let me solve this. Left side equal right side. Transfer this to second side. We got question mark equals a plus k square minus 2ak plus k square. Then expand both sides, expand it. Then add like terms. I got question mark equals negative 3a square, negative 2ak. Then substitute it into equation 2. Okay, the equation 2, come down please. It is here, g square, 2ak, 2ak. Question mark is this. Second side was this, a plus k. And now, this one telling square. And first one, unknown. Square or not, we don't know. But I am going to tell let g square in equation 1 as belong to square. Okay, then I am here. Okay, look at this. Compare equation 1 and okay. Equation 3, this one, equation 2, 1, I told it is square. Compare them. You will see is the second term from equation 3 equals to, no, I have to show you equation 1, I'm sorry. Equation 1 is this, yeah, this equation 1. S minus 3, negative 3a square, negative or minus 2ak, this one, equal to this side, comparing equation 3 and 1. 1 and 3, compare. And first term is okay in both. Second term are different. Do you think they are equal? How I know those two expressions equal? I go to grade 5 or grade 6 or grade 7. Two algebra expression, how you know they are equal? By number. But the number here has a condition. Remember, a not equal r and not equal to k. Also, I will tell a first a less than r I know less than k. Then bring numbers under those two conditions. When a3 are supposed more 4. When r4, k should be more 6, 7 million, as you like. You go with 5 and substitute in equation 4. I saw left hand side of 4 is negative 57 and right hand side of equation 4 is 1. They are not equal. Negative 57 not equal to 1. This implies that this value negative, see I took a negative outside here, negative 3a squared plus 2ak not equal to this value. Okay, I told G becomes square only. G becomes square only if we find that. But this one is not equal to that. This one is not equal to that. That means this impossible be a square. My let becomes what? Wrong. It isn't. Why? Because this is not equal to that. If those two equal by number, by substitution, I can tell, yes, this G is same of this G. Because this is square, this should be square too. But this one, the let becomes wrong, not square. When it is not square, G equal this not belong to n square. When G is not square, the root of G square at that time is also not integer. Why? G square equals 8. Square root of both sides, square root of 8 is not integer. Okay. That means the Euler perfect box does not exist. We came to second situation. When A greater, we know R smaller. Same way, put numbers A6, R should be less, see? A greater than R. Put 6. Then, when A6, R is what? 4, less than A because. K more than R. K more than R. When R is 4, K will be 5, 7, or million. But you take a small number in substitute. And substitute in number in equation equality 4. Remember that equality 4, which one? I go back, show you 4. Yes, this one, 4, is this one, 4. Negative 3a squared, negative 2ak, and substitute a and ak, then you have a number, left side. Substitute numbers here, you will get a number. Those two numbers in section 2, again, became negative 168, negative 32, left-hand side, right-hand side are not equal. Then, this will affect who? Will tell this expression is not equal to this expression because the number value after substitute were different. Then equation 1 becomes what? G square equal to that plus that not belong to n subsquare. Okay, when it is not belong to subsquare, G also becomes not integer, and then Euler perfect box does not exist. Okay, we are done from 1, but what about A equals R? I told part B, A equals what? R, and I have this condition, A smaller than B, smaller than C, and let B equal A plus R, and A equal R. Remember, A greater than R, A smaller than R. Now A is equal to R. A are equal. When A are equal, then use D only. Diagonal D by Pythagorean theorem. The square, A square, B square. And substitute B. Okay, and R is A. You got 2A here. Becomes 4A square. 1A becomes 5A square. This square is 5. D how much? Not integer. Then no perfect box. No Euler perfect box. Other possibilities. When AB equal itself, A equal B without R. Then D squared equals what? A squared plus B squared. Then we got 2A squared. Then D what? Under root of 2 is integer? No. Then no perfect box. Third, the number 4 possibility, which is D. What happens if 3 of them are equal? Then you take just one face enough, D. D squared equals A squared B squared. See, we got A squared equal to A squared. D equal A times square root of 2. No integer. D is not integer. Then no perfect box. Okay? No perfect box. And thank you very much. This was Euler perfect box. First way. And second way, I did describe it. You will see that video on YouTube later. Okay.